So thank you very much, and let me thank you first, the organizers, for inviting me here and bringing me to Morocco and actually to Africa for the first time in my life. So I enjoy this quite a lot. Concerning my talk, I had no idea that Maciek would be talking before me, and I had no idea about his topic, but in a way it connects to what was going on there, because to all these classical geometries there is a group theory side, or a Lie group theory side, and actually much of what I will be doing is connected to these symmetry groups of the classical geometries, usually in higher dimensions, admittedly. Yeah, so there is a connection to Maciek's talk in the end. Okay, so let me get more directly to the topic. Yeah, and in particular, I should say, from the point of view of group theory, Euclidean geometry is kind of an outlier, because the group of rigid motions, that's like a semi-direct product of something semi-simple and something abelian. Whereas for spherical geometry and hyperbolic geometry, the symmetry groups are semi-simple or simple. And so this will be the main setting in which I'm talking. So simple Lie algebras will play an important role here. So about the background, so Bernstein-Gelfand resolutions, or BGG resolutions, occurred first in representation theory of semi-simple Lie algebras, but it was soon realized that they have some connections to certain geometric structures, and in particular to conformal geometry, and also to the projective geometry that Maciek was mentioning. And the geometric version of these sequences, which in particular gives a construction of differential operators intrinsic to the geometries, was developed in the early 2000s in the setting of so-called parabolic geometries. And this construction is rather heavy on its geometric ingredients. So it uses tools associated to the canonical Cartan geometry that you get for each of those geometric structures, like tractor bundles and tractors and tractor connections. So it's not easily accessible. However, if you start with Riemannian geometry or pseudo-Riemannian geometry, you actually always get two underlying structures, or weakening of the structures, that are parabolic geometries. Namely, on the one hand, of course, a Riemannian metric or a pseudo-Riemannian metric, of course, has an underlying conformal structure if you just look at the metric up to scaling that depends on a point. But it also has, as Maciek was saying, a projective structure which is based on the family of geodesics viewed as unparametrized paths. All right. And so somehow whenever you start with a Riemannian manifold, there is all this geometry and all these BGG sequences in the background. And there is the question, can you make this more explicit? And actually the input for this, or the motivation for this, came from the fact that recently BGG sequences started to play quite a role in applied mathematics, and people are seriously trying to compute in this setting. And the value of the construction here is this starts from differential forms. In general, it will be differential forms with values in a vector bundle. But if you look, say, at domains in Rn, then all these vector bundles are trivial, so it's just families of differential forms. And in the last years, the applied mathematicians have learned quite well how to deal with real value differential forms. And so finding constructions for more complicated operators in terms of differential forms became of big interest. And actually, in recent work, we gave a simpler version of the construction in the setting of... Noise. Thank you. We gave a simpler version of the construction for domains in Rn with the flat metric that is there. Thank you. And this construction works in low regularity, but this will just be important for the point of view of motivation here. And in the smooth case, this easily extends to general Riemannian manifolds, and I will outline this construction for Riemannian manifolds with a focus on the conformal case. So I will almost exclusively talk about the conformal situation and just make a few remarks on the projective case in the end. I should also say I'm kind of focusing on the general theory and not starting from examples or anything like that. And to some extent this is intrinsic to the topic, because we start with semi-simple Lie algebras, which is something that exists from the beginning, that is there, and we start with irreducible representations, and there is a list of semi-simple Lie algebras and there is a list of irreducible representations, and you cannot slightly change a semi-simple Lie algebra or anything like that. Okay, but I'll try to make some connection to examples, including the Roger-Liouville problem that Maciek was talking about. Okay, so basic contents. I will start going through the algebraic background and setup, and then I'll discuss the BGG construction in the setting of Riemannian geometry. Okay, so for this whole thing, the perspective and the way to do things is very important, because it's like what you can do is you can deal with a large variety of situations if you don't try to make things too explicit. So if you use the right terminology and the right concepts, then this works in a very general setting. The background I'm using here is, which is well known, is that natural vector bundles in Riemannian geometry are closely related to representations of the orthogonal group ON. So indeed, if you start with a Riemannian, and the same story works for pseudo-Riemannian, but I'll restrict to the Riemannian case for simplicity. So if you start with a Riemannian manifold, you look at its orthonormal frame bundle, and then whenever you have a representation of the orthonormal group, of the orthogonal group, you can look at the associated vector bundle. And now the basic properties that you have here is, first of all, you can view the Levi-Civita connection as a principal connection on the orthonormal frame bundle. Then it induces linear connections on any associated vector bundle. And I'll denote all these connections by nabla because they are all from the same origin, and it's a consistent notation. Maybe less well known, if you have equivariant maps between representations, they of course induce natural bundle maps between the corresponding induced bundles. And in particular, whenever you have a representation of the orthogonal group, you can take the infinitesimal representation of its Lie algebra. So you get the infinitesimal representation which is bilinear from On times W to W. And this induces a bilinear bundle map that will play an important role in what I'm doing, and I'm denoting it by a fat dot from skew-symmetric endomorphisms of the tangent bundle times Wm to Wm. Okay, and one indication of why such an approach is useful, you can see if you look at the Riemann curvature tensor. So you can view this as a two-form on M with values in skew-symmetric endomorphisms of the tangent bundle. And then if you want to know the curvature of the induced connection on Wm, then it's always characterized by a universal formula. So on the left-hand side you have the standard definition in terms of covariant derivatives. And this can be written as curvature of psi and eta acting on sigma. And what this acting on sigma explicitly means depends on what the representation is or what the bundle is. Yeah, so this is like, you know, the formula if you look at the action of curvature on a tensor field, you have to act on each index separately. So this is all absorbed in the notation here. Okay? Right. And now, as I said originally, the main input for the construction comes from Lie algebra theory. And for our purposes, the role of Lie algebra theory is that it produces interesting representations of the orthogonal group, which come with some additional ingredients. And what I'm doing here is kind of embedding the orthogonal group in a bigger Lorentzian orthogonal group, which you probably have seen if you have heard something about conformal geometry, because this is exactly the infinitesimal the conformal isometries of a sphere. So what I do is I start with an integer greater or equal to 3, because conformal geometry in dimension 2 is notoriously different. And I consider Rn plus 2 with a basis numbered from 0 to n plus 1. And then I put in Lorentzian inner product on this Rn plus 2, for which the first and the last basis vector are what is called among physicists light cone coordinates. So these are light-like vectors. And the remaining ones form a standard Euclidean Rn. Okay? And so if I take this inner product and I take its orthogonal group, so this is isomorphic, and I will just say equal to ON plus 1, 1. But of course, if you fix E0 and En plus 1, then you just have a orthogonal transformation of the remaining n basis vectors. So you can naturally view ON as a subgroup in G of those elements that fix two vectors. And if I write things out in matrices, then it's actually easier to do this for the Lie algebra rather than for the group. And if I do that, then I should decompose my Lie algebra in blocks of size 1, n, and 1. So this just emphasizes the spatial role of the first and the last basis vector. And then you just compute that you get matrices of this form. And you see there is an element of Rn here. There is a column vector which I interpret as an element of Rn star. And the big A in the center represents the orthogonal group as a subgroup. And the A's are like representing dilations, or the infinitesimal dilations. Okay. And now it turns out that if you think about matrices decomposed into blocks, this is somehow compatible with matrix multiplication. Therefore, it's compatible with the commutator of matrices. So you can view this as a decomposition of G into three components that I call G minus 1, G0 plus G1. So G0 is the block diagonal part. G minus 1 is the bit below the block diagonal, the bit below the main diagonal, and G1 is the bit above the main diagonal. And then you immediately compute that this is compatible with the Lie bracket, in the sense that if I bracket Gi with Gj, then I land in Gi plus j. And this gives what is called a one grading on this Lie algebra. And such one gradings are classically very well understood because they are related to the classification of Hermitian symmetric spaces. So that's something that is well understood from a structural point of view. Okay, so now I said that this is related to conformal geometry. So how can this be seen? Now, yeah, in fact, you can just look at the restriction of the bracket. Yeah, because bracketing with G0 preserves degrees. So you get a bracket from G0 times G minus 1 to G minus 1. And on ON, this just gives you the standard action. And in addition, you get multiples of the identity. So this bracket actually identifies G0 with the conformal Lie algebra in dimension n. And then it turns out that the action on G1, which I strategically identified with Rn dual, really is the dual of the standard action on Rn star. Okay. And now it will be very important. So if you remember, this block decomposition just came from the decomposition that I singled out the first and the last basis vector. So actually it came from a decomposition of the standard representation of the group G. And now if you think about the basic ideas of representation theory, how do you construct representations? You apply tensorial operations to the standard representation. And in fact it turns out, and you can phrase this much more conceptually in terms of Lie theory, that these kinds of gradings are available on all representations of the group. And here for simplicity I restrict to irreducible representations. Okay? So in fact, if you start with any irreducible representation that I call V, it canonically decomposes into a direct sum of some lengths, so I from 0 to capital N. And this is characterized by the fact that if I act infinitesimally, then the components of G move you in the grading according to their own degree. So Gi maps Vj to Vi plus j. Okay? Right. So, in particular, if you act with G0, then you keep each of the degrees. And, right, so I can, if I take my representation V and restrict it to the subgroup On, then each Vi will be invariant. And hence, if we form associated bundles, then the associated bundle to V, which I'll denote by Vm, or calligraphic Vm, again decomposes into a direct sum of components. Right? Yeah, so at the moment it may seem unreasonable to do this, because why are you putting together all these different kind of natural bundles? But this will become clear now, because you see we have the actions of G minus 1, which lowers degree by 1, and if you pass to associated bundles, I'm too early, but you see G minus 1 was coming from the standard representation, so if you form the associated bundle, you get the tangent bundle. And G1 comes from its dual, so you get the cotangent bundle built into the situation. And now you have this infinitesimal representation not only of G0, but also of G minus 1 and G1. And what this gives you, so if you restrict the infinitesimal representation to each of the components Gi, so first of all, most easily for I equals 0, this gives an extension of this bundle map fat dot from O of Tm to CO of Tm, yeah, in an obvious way, and this preserves each of the grading components. But in addition, I obtain bilinear bundle maps, which I again denote by a fat top, because they all come from the same source. And one of them is defined on Tm times Vm to Vm, the other one on T star m times Vm to Vm. But now these do not preserve the decomposition, but Tm maps you down one index, so it maps Vj to Vj minus 1. T star m maps Vj to Vj plus 1. Yeah, so in addition to this family of natural bundles, you can move in the sum in one direction using an element of the tangent bundle or a vector field, and in the other direction by using an element of the cotangent bundle or a one form. Okay? Right. And so these fat dots are bundle maps. So in particular they induce maps on sections. So if I have a vector field and a section of Vm, then I again get a section of Vm, and I will denote also these induced tensorial operations by the fat dot. So in particular, if I have a vector field eta and a one form alpha and a section, say Sj in gamma Vjm, I can act with eta to get a section of Vj minus 1, and I can act with alpha to get a section of Vj plus 1. All right? And as I said before, these bundle maps coming from equivariant maps, they are automatically parallel for the Levi-Civita connection, which in this section, in this setting, just means that if you take a covariant derivative of such an expression, eta acting on Sj, you just have a Leibniz rule. So this gives the Levi-Civita the covariant derivative of eta in direction psi acting on Sj plus eta acting on the covariant derivative on Sj. Yeah, so you can compute with these things very easily and very nicely. Okay. Right. Now this is maybe a slide which is the details are not important. I just want to convince you that you can easily make things explicit. Yeah, but what they look like explicitly may be very different depending on how you start your representation. So for example, if you start with the standard representation Rn plus 2, then we already know that its decomposition is R plus Rn plus R. So if you look at sections of the corresponding bundle, this will be a function here, a vector field or a one form here, and a function there. And I've chosen to use the identification with one forms. So I write such a section as a triple f phi h with f and h smooth functions and phi a one form. And then you can easily make these operations explicit. So if you act by a vector field psi, yeah, what you get is you get your vector field plugged into the one form, and you get the function multiplying, or this is badly visible, so this should be psi b, so that's the one form associated to psi via the Riemannian. Yeah, and you can see that somehow you move to the left by one row, which exactly expresses that you map Vj to Vj minus 1. And if you use the action of the one form instead, then you just get f times alpha and the metric of alpha and phi, and moved in the other direction. Yeah, moved to the right rather than to the left. Yeah, so, and all the operations that you use are very basic, so they are standard Riemannian invariant operations that one knows how to deal with. Yeah, and if you know how to handle the standard representation, you can in principle go through all these tensorial constructions and make things explicit for any irreducible representation you like. And I just want to do this. Well, I don't really want to do it, but I want to mention a second example which will be important in what follows. So if I take the second exterior power of the standard representation, then this is isomorphic to the adjoint representation. Yeah, so that's just O n is isomorphic to lambda 2 of Rn. And so then my decomposition into three parts just as it comes from the original decomposition of the Lie algebra. So sections are a triple of a vector field, a skew-symmetric endomorphism of the tangent bundle in the one form. Yeah, this is just what is written here. And again, you can write the operations in a simple fashion, but here it's and in fact this is really the operation that is induced from the Lie bracket viewed as a map from g minus 1 times g1 to g0. Yeah, and that's the way how you then act on a vector field. Yeah, and again it just uses standard operations. Yeah, plug the vector field into the one form, multiply by zeta, plug zeta into the one form, multiply by psi, and take the dual of the one form as a vector field. Yeah, and it's just a nice combination. And then the operations can be all expressed in, yeah, so here you have a vector field, here you have an endomorphism of the tangent bundle, you just plug in. Vector field one form, you get this bracket. One form vector field, you get this bracket. Endomorphism one form, just compose in an appropriate way. Yeah, so all these are very, very natural and simple operations if you want to make them concrete for a specific bundle. Okay, and having this at hand, I can basically get to the Riemannian BGG construction. And now this works as follows. Okay. Yeah, so I need one more ingredient which is always popping up when you're dealing with conformal geometry. So if I have a metric G on M, there is the so-called Schouten tensor. And for all purposes, this is just an equivalent encoding of Ricci. Yeah, so it's like the Ricci curvature, but slightly different factors multiplied in. So actually the defining equation is that Ricci is n minus 2 times Schouten plus trace of Skalton times G. Yeah, so if you want, you can decompose Ricci into a trace term and a trace-free term, and Skalton into a trace term and a trace-free term, and then they are related just by different multiples. Yeah, so it's a nice way to encode the Ricci curvature. And the reason why it is a nice way, a nice encoding of the Ricci curvature, is that in this way you can very nicely write out the decomposition of the Riemann curvature tensor into simpler parts. And indeed the formula is here. So the Riemann curvature with two vector fields plugged in, acting on a third vector field, is given by the Weil curvature. Yeah, so this is the trace-free part of Riemann. And the difficult bit is always to include the trace part in an appropriate way. And here's the way that you can do using Skalton and using this operation that I introduced before. So you just take the bracket of the vector field psi, yeah, so this algebraic bracket of the vector field psi with the one form rho of eta minus the bracket of eta with the one form rho of psi. Yeah, and this encodes all the trace part in the Riemann curvature tensor. Okay, and if you want, you can further split this into the trace-free bit of Skalton and the trace part. Right? Okay. But now there is a quite important feature, because this, yeah, once it's written in that form, it's obvious that it extends to any associated vector bundle. Because now if you start with your representation decomposed in the direct sum, we have the Levi-Civita connection, which acts. Sorry, I got ahead of myself. So I can now already do the first step in the BGG construction, which is the following. So we take our representation, decomposed into a direct sum of ON invariant subspaces in a specific way. Then, of course, on sections of this, you have the Levi-Civita connection, and since the VI are ON invariant, the Levi-Civita connection just acts component-wise. Okay, so the Levi-Civita connection preserves components. But now I can modify this component-wise Levi-Civita connection by tensorial terms that come from the additional operations that I get in this situation. And that's exactly the formula here. So what I called nabla V psi of S is just the component-wise Levi-Civita connection plus the action of psi minus the action of rho of psi. Right? And the minus I have here is just to comply with the usual sign conventions for the Skalton tensor. Okay? But now you see this first bit is component-wise, but the other two bits are not. They mix different components. So in fact, if I want to make this explicit, I can look at the i's component of the derivative. It's the Levi-Civita component, the Levi-Civita derivative of the i's component of S, plus psi acting by the on the I plus first component, minus rho of psi acting on the I minus first component. Yeah? And that's the key to the further developments, because now I have tensorial operations moving between the levels, and I have differential operations preserving the levels. And the trick about all the forthcoming things is that there is a possibility to trade homogeneity for differentiability in a way. Yeah, so you can look at lowest homogeneous components and their things become simpler, and then you solve for the lowest homogeneous component, and you do this iteratively, and you get a way how to solve very complicated equations in a way. Yeah, and it's all done by invoking these operations. Okay. But the first thing I have to do is I have to understand the curvature of this connection. And in particular, I want to prove that this connection is flat, provided that your metric is conformally flat. Yeah, so even for a non-flat metric, you can get a flat twisted connection here, provided that the metric is conformally flat. Okay? And actually, the computation to do this is not really difficult in the complete generality of arbitrary irreducible representations. You can just start from this formula, yeah, and expand the definition of curvature of a linear connection, right? And so what you do, yeah, this is like nabla psi of nabla eta minus nabla eta of nabla psi minus nabla of the Lie bracket of the two. Yeah, and you can you can just expand this formula explicitly. Yeah, and if you remember, we exactly know how to differentiate such expressions because we know that there is a Leibniz rule for those, and so on and so forth. Yeah. So the first thing that you see is, okay, so if you take one derivative, then the i's component depends on the components I plus 1 and I minus 1. So if you take two derivatives, you get additional dependencies on I plus 2 and I minus 2. Right? So you see that if you apply the curvature of psi and eta to S, then the i's component of the result can depend only on the j's component of S for j from I minus 2 to I plus 2. Okay? And now it's very easy to eliminate some of these pieces. So if you check what may happen if you start with I plus 2, then the only option is you act with psi on Si plus 2 and then you act with eta on the result, which you get from the second term with a minus, and from the first term you get psi acting on eta. But we know that psi acting on eta acting on S is eta equals eta acting on psi acting on S, because we come from a representation of an abelian Lie algebra. Yeah, so this follows from properties of this Lie bracket. And in the same way, if you act with rho psi and rho eta, these two actions commute. So again, there will be no contribution. So there is actually no dependence on Si minus 1 and no dependence on Si plus 1, and we're just left with the dependencies on Si plus 1 and Si minus 1. Okay? Okay. Next, it's rather easy. So to be on the safe side, I've copied the definition up here in order to help me argue. So if I look at the dependence on Si plus 1, what may happen? I can differentiate, I can first act with psi and then differentiate in the direction eta, or differentiate first and act, and then you just collect the terms, you arrange them, and you see that torsion freeness implies vanishing of this part. Okay, so there is no dependence on Si plus 1. So there is only dependence on Si minus 1 and Si. For the dependence on Si minus 1, so what can you do? You can first act with a Skelton tensor and then differentiate. Or you can first differentiate and then act with a Skelton tensor, and then this comes as a kind of a commutator. And so what you find out is that what you get is just the so-called Cotton-York tensor, which is just given by nabla psi rho of eta minus nabla eta rho of psi minus rho of the Lie bracket. This exactly corresponds to the three terms in the decomposition of curvature. So this is the so-called Cotton or Cotton-York tensor, and you just get the Cotton-York acting on Si minus 1. Okay? So that's the first non-trivial contribution to the curvature of the twisted connection, coming from the Cotton tensor, which is well known to vanish for a conformally flat metric. Okay. And for the second part, it's a bit more complicated, because to start with S0, you first have the terms in which you differentiate twice, which will just give you the action of Riemann. And then you have the terms in which you start acting by psi and then act by rho of eta, or the other way around. Okay? So what you have to understand is these mutual actions of vector fields and one forms. Okay? And here it becomes really crucial that we deal with a representation of the whole Lie algebra. Because what happens here is, I said this already, this operation with the curly brackets, this comes from a part of the Lie bracket in the Lie algebra G. And so, in particular, if I look at my relation between Riemann and Weil, which is here, yeah, this is just the standard of the action on the tangent bundle. So this extends to any kind of induced bundle. Okay, so I can take here any section S of an induced bundle, write bullet, 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 and I get the correct formula for the decomposition on any induced bundle. Right? But if I really come from a representation of G and not just of G0, I can expand this bracket, which gives the action of a Lie bracket of two elements, into the commutator of the iterated actions. Yeah, and if you do that, you readily run into the formula that's here. Namely, yeah, you get Riemann from these terms, you get something like the commutator of iterated actions from that terms, and things are arranged in precisely the right way, so that only the Weil curvature term remains. And so you come to the theorem that if you look at the curvature of this connection nabla V on S, this is just given by the action of the Weil curvature, which preserves slots, plus the action of the Cotton tensor, which moves you up by one index. Okay? And so, in particular, you see that in each dimension, this connection is flat, provided that the metric is conformally flat, because then both Weil and Cotton will vanish. Okay? Right. And now the rest is relatively simple. Yeah? That's now almost mechanical in a way, or at least the next step to get to what we call the twisted complex. So whenever you have a linear connection, you can couple it to the exterior derivative to get what is called the covariant exterior derivative. Yeah, and this is just given by the same. You take the formula for the exterior derivative given in terms of differentiating by vector fields and Lie brackets, and replace the differentiations by vector fields by a covariant derivative, then you get the formula for the covariant exterior derivative. Okay? So in particular, you obtain the nabla, which is just the covariant exterior derivative for the Levi-Civitard, and the nabla V, which is the covariant exterior derivative for the twisted connection, and they both act on differential forms on M with coefficients in this bundle Vm. And now, of course, if I have a differential form with coefficients in Vm, I can again decompose it into components, and then it's easy to get an explicit formula. And it's very similar to what we had before. So the ith component of the covariant exterior derivative with respect to nabla V is just the component-wise covariant exterior derivative for Levi-Civitard plus two operations. Here I call it tail because it's actually induced by a Lie algebra cohomology differential, and an operation that is called tail rho, which is again related to a Lie algebra cohomology differential, and they are just given by plugging in all vector fields except one, acting with this additional one, and alternating the result. Respectively, plugging in all vector fields except one, acting with rho of that one, and then alternating. Right? So you get a simple explicit formula, provided that you are willing to use these bullet operations, then this works completely uniformly for all representations. Okay, now of course, in particular, this tail is a pointwise operation. So it is actually induced by bundle maps, which map lambda k t star m tensor vi m to lambda k plus 1 t star m tensor vi minus 1 m. So I've just taken into account the change in homogeneity. and we will denote these bundle maps by the same symbol. Yeah, so this is just a tensorial operation on sections induced by the bundle map, denoted by the same symbol. And then, as I said, this comes from a Lie algebra cohomology differential, and if you don't know it, it's also easy to prove this by hand in a few lines, that if you apply delta twice, you get 0. And so here you get natural subbundles, image of delta sitting in kernel of delta in each degree. Okay? Right, and now I'll get a bit sketchy, actually. So now what you can do is, on each of these representations you have a canonical inner product as a representation of ON, and so now in there you can define the kernel of delta, which contains the image, so you intersect it with the ortho complement of the image. If you want, or if you know the story in some other settings, this is just a representative for the cohomology of delta. Okay? And actually this space is HK, which sound a bit like harmonics. They correspond to Lie algebra cohomology groups, and these Lie algebra cohomology groups can be computed explicitly in terms of representation theory using an old theorem of Constant from the 1960s. And there is one very important thing to realize: these cohomology groups form an amazingly small part of the differential forms with coefficients in Vn. So just to give you an indication, here in the setting of conformal geometry, this HK can either be irreducible, or it can consist of at most 2 irreducible components. So in particular, you just have to think about we are in this space. Yeah, like lambda k, t star m tensor Vm, the whole Vm. Yeah, and an irreducible representation, whoops, can sit in at most of one of these components Vim. So all the others do not contribute, and again it will be just a very small part of this. Yeah, so these harmonics are extremely small subspaces. Okay? Right, and now the rest of the construction actually is just playing with homogeneities, looking at lowest homogeneous components. And I mean, I won't manage to go through this in detail, but that's not really difficult, and there is no conceptual input, it's just computing more or less. So what happens is, in each degree, this delta defines a homomorphism from the ortho complement of its kernel onto its image. Yeah, these are just finite dimensional maps. Okay? And now you can define an inverse in quotation mark to that. So you can take the inverse on the image of delta and 0 on its ortho complement to define a bundle map T. Okay, and then you see from this definition it follows immediately that delta composed with D composed with delta is delta, and T composed with delta composed with T is T. T composed with T is 0. Kernel of T is image of delta perp, image of T is kernel of delta perp. Yeah, these are just obvious observations. And if you go to examples, then making this T explicit is as easy or difficult as making this delta explicit. Yeah, so in simple cases you can just read it off by hand. In more complicated cases it needs more substantial computations. Right. Let me see how I'm doing time-wise. Okay. So the key of the BGG machinery is that now whenever you have a section of this harmonic part, you can canonically extend it to a differential form. And the fact is that this extension is given by a complicated higher order differential operator, but it admits a very simple first order characterization. Okay? So there is a unique form S of phi which is completely characterized by the fact that the difference between S of phi and phi is in the image of delta, which means that if you think about cohomology, S of phi is a representative of the cohomology class determined by phi, right? And this representative is characterized by a simple first order equation, namely if you take the covariant exterior derivative with respect to the twisted connection and then apply t, you get 0. Yeah, so there's a first order differential equation characterizing this S, right? And yeah, I mean, I have actually prepared a sketch of proof, but I think I will skip the sketch of proof. The ideas are always the same. You look at what happens to the lowest homogeneous component, and then you see that the lowest homogeneous component behaves in a much simpler fashion than the general operation, and then you show that you can correct component by component in order to get representatives and make them linear. Yeah, so I'll skip through this sketch of proof. Okay, and now we are ready to define these so-called BGG operators. So what you do is you have your phi, which is a section of the harmonic part, and we can form its so-called splitting operator. This is what we call the S. If we differentiate this, we land in the kernel of T, which is the image of delta perp, and so we can take its component in hk plus 1. And this is what defines the BGG operator. Okay, so in particular, it is very easy to see that in degree 0, you get this harmonic part is just the component V0. Yeah, it's just the lowest component if you want. And in particular, you get an operator D0 acting on these sections of V0 of n. And it turns out, first of all, this operator can be of any order depending on the representation you choose. Right? It can be of any order r greater or equal to 1. And if you know this order and the representation V0, then they uniquely determine V. So in a way, if you want, you can view all these BGG sequences as being indexed by certain differential operators defined on these spaces. And it turns out that for V0, you can get any irreducible representation of ON. So on any natural bundle coming from an irreducible representation, you get operators on all orders, and if you choose one of these orders, then you get a unique BGG sequence containing this as the first operator. And it's actually easy to see what this first operator is. You just take an r-fold covariant derivative of your section, symmetrize, and then project to the principal part, which is, in the sense of representation theory, the most significant irreducible component. And if you do that, what you get, for example, is you get all types of conformal killing operators, conformal killing Diano operators for order 1. If you do the projective version, you get the operator that recognizes Riemannian Levi-Civita connections in a projective class, which is related to this Roger-Liouville problem that Maciek was talking about. And actually the Roger-Liouville problem consists in very carefully analyzing the first BGG operator and finding necessary and sufficient conditions for existence of a non-trivial element in the kernel. Right, so let me briefly skim through some applications. So of course, if G is conformally flat, then these twisted forms with the twisted covariant exterior derivative is a complex, because if you couple a flat connection to the exterior derivative, you get a complex. And it's a final resolution of the sheaf of local parallel sections of Vm. Yeah, and Vm just decomposes into a sum So this is about as much as you can know about the cohomology on a Riemannian manifold, right? So in a way, if G is conformally flat, then the cohomology of this twisted complex is understood to some extent. And one easily verifies that in this conformally flat case, the splitting operators actually intertwine between the twisted complex and the twisted covariant exterior derivative and these BGG operators. So in this case also the BGG sequence is a complex and it computes the same cohomology. Right. Some of these parts extend to the curved case. So in particular, if you are in the flat case, then the kernel of this first BGG operator is exactly equivalent to the space of parallel sections for the bundle Vn. And what this does is it provides a rewriting of the first BGG operator in first order closed form. And you can interpret this BGG complex as a compatibility complex for this rewriting of the first BGG operator in first order closed form. And in particular, if you start with the adjoint representation, this produces the conformal deformation complex. And if you go to general metrics, so not conformally flat, there still is a pretty close relation between the twisted complex and the BGG complex. In particular, one can still rewrite the first order BGG operators in first order closed form using modifications of this twisted connection, but this is getting complicated. And it's getting complicated enough to cause effects like Maciek was saying that in dimension 3 the Roger-Liouville theorem or the Roger-Liouville problem is still an open problem. And in addition, there are many applications of BGG sequences to topics like conformally compact matrix, which is like the higher dimensional analog of the sphere bounding the hyperbolic disk, or the circle bounding the hyperbolic disk, and so on. Okay, yeah. So let me conclude with very few remarks on the projective case. Basically, if you view things the right way, the projective case goes completely parallel to what we've done here. So in this case, the initial Lie algebra is a different one. It's SLN plus 1R, and there is a simple grading which has an analogous form to what we had for this SO. So we had Rn plus GLN R plus Rn dual. And in fact, this is the Lie algebra of projective transformations of a sphere, and so on and so forth. And so there is the projective geometry construction of BGG sequences, and there is a simplified construction for smooth manifolds endowed with a torsion-free connection on the tangent bundle, which in addition preserves a volume form. And if you do that, then the whole development is very similar to what we had here. You can use your connection, you get an action of the tangent bundle, you get an action of the cotangent bundle, you get a decomposition of the curvature into trace-free parts, which can be phrased in completely similar style to what happens here. And if you do this to the Levi-Civita connection, you can apply it in Riemannian geometry, and then among the resulting first BGG operators, you get the killing operators on all types of tensors, in particular the killing operator on vector fields, and one obtains a version of the Riemannian deformation sequence. Yeah, the drawback of this projective case for the Riemannian situation again relates to something that Maciek was saying, namely complexes and resolutions here you get only for projectively flat connections. And while general linear connections on the tangent bundle there is a large supply of projectively flat ones, for Levi-Civita connections projective flatness is equivalent to constant sectional curvature, So complexes are available only in a very restricted setting here. Okay, so that's all. Thank you very much.
Thank you very much.